Section 14.2 is finding limits using algebra techniques. So pause the video and go ahead and copy down these notes. The first thing is, if possible, plug in your x-coordinate. So that's what this one says here. The limit as x approaches a of x is just a. So if there's no domain issues, plug in your x-coordinate just like you would if you were trying to find the y-coordinate for that function. So if possible, just plug it in. The limit as x approaches a of a constant is just that constant. If you're adding or subtracting inside a limit, you can split it up and add or subtract the limits. If you multiply inside of a limit, you can split it up and multiply the limits. But again, if possible, just plug in your x-coordinate. If there's domain issues, then we'll have to do some algebra to talk about those. So here's this first example. It says the limit as x approaches -1 of 6x to the fifth minus 5x to the cubed plus x squared minus x minus 4. This has no domain issues. It's just a polynomial. So if I plug in -1, it's not going to blow it up. It's not going to make a denominator 0. It's not going to have a negative inside a square root or anything like that. So this is the case where if you can plug in the x-coordinate, just plug in the x-coordinate. As soon as you plug in the x-coordinate, you can drop the limit notation. Anytime there's still x's in it, you need the limit notation, but as soon as you plug in the x value, you can drop it. So I plugged in the x value, and now I'm just going to simplify. So you end up with -6 plus 5 plus 1 plus 1 minus 4, or a -3. So in this case, the limit as x approaches -1 and the y-coordinate at x equals -1 are the same thing. And that will happen most of the time, especially for polynomials and such. So go ahead and pause the video and try this next one. So again, if I plug in 2 for this, it's not going to make a denominator 0, it's not going to make a negative inside a square root or any other domain issue, so I can just plug it in. So I plug in 2 for x, and you end up with the square root of 125, or 5 root 5. So here's one. We have the limit as x approaches -2 of this function, and on this one, I can't plug in -2. It's not in the domain. If I plug in a -2, you get 0 in the denominator. So when you have something like this, the first thing you always want to check is to see if you can factor it. So this one does factor, so go ahead and pause the video and factor this completely. So one thing when you're doing limits, you have to keep this limit notation for as long as you haven't plugged in this x-coordinate. So I haven't plugged in x yet, all I've done is factored the function, so you have to keep this limit notation. Versus on the previous example, I immediately plugged in x, so you can drop that limit notation. But this limit notation needs to stay the entire time. It would be like dropping your square root or your squared on a regular function. So here we have x cubed plus 8 is a sum of perfect cubes. So you get x plus 2 times x squared minus 2x plus 4. X squared minus 4 is a perfect square minus a perfect square. So you get x plus 2 over x minus, or times x minus 2. So as you can see, you have the same factor in the numerator and the denominator. So you can cancel those. This is a whole. X equals -2 is a whole for this function. So you can cancel these factors off. Now you want to check, now can I plug in this x equals -2? So now if I plug in x equals -2, there's no more domain issue now that I've canceled off this factor of x plus 2. So go ahead and pause the video and plug in -2 and find this limit. So as soon as I plugged in x equals -2, now you can drop that limit notation because now you're just working with the numbers. You've applied this function, you don't need it anymore. So we plug in -2, you end up with 12 over -4, or a -3. So what is this for this graph? What does this mean? You can't plug in x equals -2. It's not in the domain of this function, but you could cancel this factor and still get a number. So this is actually our whole. We've done wholes back in chapter 3. We canceled the factor, plugged it in. This is exactly the same thing. We have a whole here, and that's what the limit is equal to, is it's equal to the y-coordinate of the whole. So here's another one that we can't plug in x equals -2. We want the limit as x approaches -2 of this function. It would make the denominator equal to 0, so we can't do it. On this one, you can't just factor the numerator and the denominator to cancel a factor, so we have to do something else. When you have these square roots in the numerator, we want to get rid of them, so we're going to actually multiply by the conjugate of the numerator. So I wanted to get rid of the square roots in the numerator, so I multiplied both the numerator and the denominator by the conjugate of the numerator. So I multiplied both by the square root of 2x plus 7 plus the square root of 3. In the numerator, that just cancels out all your square roots. You end up with 2x plus 7 minus 3. In the denominator, I just left those multiplied together. I didn't FOIL anything out. I just left it that way. So now, let's go ahead and pause the video and simplify the numerator and see what you get. So if you simplify the numerator, you get 2x plus 4. If you factor out a 2, you get this x plus 2 factor. So you get this factor that we need to cancel from the denominator. So now we can cancel off this factor that's making us not be able to plug in x equals negative 2. And now we can plug in x equals negative 2. So go ahead and pause the video, plug in x equals negative 2, and find this limit. So now if we plug in x equals negative 2, now that we've canceled off this factor, you end up with 1 over the square root of 3. So whenever you have these ones with the square roots in the numerator, go ahead and multiply both the numerator and the denominator by the conjugate of the numerator, and that denominator will probably now cancel out. So now we have one that says limit as x approaches 0 of sine squared x plus sine of x times cosine x minus 1 all over x squared. So I put a little reminder right here that we found in 13.1 that the limit as x approaches the sine of x over x is equal to 1. Another one that we need to have memorized is that the limit as x approaches 0 of the cosine x minus 1 over x is equal to 0. So these are going to be important. So on this one, we're going to use some of our properties of limits to split things up. So when I look at this, the first thing I see is that I can factor out a sine of x. So what I'm looking for is to be able to use these, some combination of these, and adding and subtracting different limits to be able to evaluate this limit that I can't just do by plugging in 0. So I factor out a sine of x, and then you get sine of x plus cosine x minus 1. I'm keeping that together because I know that's one of my ones that I have memorized. So now x squared is the same thing as x times x. So I can split this up into a multiplication of limits. So I had the sine of x over x times the sine of x plus cosine x minus 1 over x. So I split that up into the multiplication of two different limits. That was one of the properties on the first slide. So this one is one that I have up here, so I can keep that one. This one here, I notice, is a sum of the two that I have up here. And we had another property that said if you add 2 inside a limit, you can split it up and just add 2 limits. So I have the sine of x over x, which is one that I know, and I have the cosine x minus 1 over x, which I know. So I split this limit of sums into a sum of limits. Now I know all three of these limits, and I can just evaluate this. So this limit as x approaches 0 of sine of x over x is 1. Again, same thing, is 1. And then the limit of as x approaches 0 of cosine of x minus 1 over x is 0. So then if I just evaluate this whole thing is equal to 1. So this is just using our properties where we split up. If you multiply inside a limit, you can split it up and multiply the limits, and then same with add or subtract. So we want to find the limit as x approaches c of the average rate of change from c to x. So remember, average rate of change is slope, so that's just f of x minus f of c over x minus c. So we want to find the limit as x approaches 2, in this case, of this. So go ahead and pause the video and set that up. So we end up with the limit as x approaches 2 of f of x minus f of 2 over x minus 2, which if you evaluate that, you get the limit as x approaches 2 of x squared plus 3x minus 10 over x minus 2. So on this limit, you can't just plug in 2 because it makes the denominator 0, but the numerator does factor. So go ahead and pause the video and factor the numerator to then evaluate this limit. So the numerator factors into x minus 2 times x plus 5. So now we have this x minus 2 factor in both the numerator and the denominator. We can cancel those off. Now you can just plug in 2. So the limit as x approaches 2 of this average rate of change is 7. So remember, when you're solving limits algebraically, always the first step is just to see if you can plug that x coordinate in. If you can't, then you need to use some kind of algebra to manipulate the function to then be able to plug that x coordinate in.